Hello, and welcome to Sleepy Engineering. In this video, we will explore the complete history and discovery of one of the most powerful forces ever understood and harnessed by humanity: electricity. This narration is intentionally slow, detailed, and repetitive. It is designed to help you relax, focus, or fall asleep. There will be no sudden sounds, no music, and no emotional tone. Only the steady voice of information. Now please sit back, close your eyes if you like, and let the story of electricity begin. Long before electricity became a science understood and controlled by human beings, ancient civilizations were already fascinated by mysterious natural forces that they could not explain. And among the most striking of these phenomena were static electricity and lightning, which seemed to reveal hidden powers within the world. The earliest recorded observations date back thousands of years to the ancient Greeks, who noticed that when amber, a fossilized resin, was rubbed with animal fur, it would attract light objects such as feathers and dried leaves. This strange property was puzzling and became the basis for the very word electricity, which derives from the Greek word electron, meaning amber. Though the Greeks had no scientific framework to explain what they witnessed, they understood that something invisible was being transferred, and that it had the ability to move matter without physical contact. At the same time, lightning was one of the most awe-inspiring and terrifying natural forces experienced by early humans. Storms would illuminate the sky with brilliant flashes of light, followed by deafening thunder, and the sheer destructive power of lightning strikes was often interpreted as a sign of divine anger or celestial power. In Greek mythology, lightning bolts were the weapons of Zeus, while in Norse mythology, Thor wielded thunder and lightning with his hammer. Cultures across the world, from China to the Americas, attributed lightning to gods or spirits, which shows how universal and powerful this natural phenomenon was in shaping human imagination. Although these early encounters did not lead to systematic experimentation, they reveal how electricity captured human attention long before it could be studied scientifically. Other ancient cultures left evidence of possible experiments with electrical phenomena, though historians debate their true purpose. The so-called Baghdad battery, discovered in Mesopotamia and dated to around 2,000 years ago, is a clay jar containing a copper cylinder and an iron rod, and some researchers suggest it could have been used to generate a small electric current when filled with an acidic liquid, such as vinegar. Whether it was truly a battery or simply a container is still uncertain, but the possibility suggests that humans may have stumbled upon the principles of electricity far earlier than we normally assume. In addition, ancient physicians in Greece and Rome used electric fish, such as the torpedo ray, to treat pain by placing the live animal on a patient's body, so that its natural electric discharges could numb the sensation. Scribonius Largus, a physician to the Roman Emperor Claudius, wrote about this practice in the 1st century, noting its usefulness for treating headaches and gout. While these methods were empirical rather than scientific, they show that people were aware of electricity's existence, even if they did not understand it. The role of amber in early experiments is especially important because it revealed the principle of static electricity long before modern instruments existed. When rubbed amber not only attracted small objects, but could also produce tiny sparks and even a faint crackling sound. Ancient observers sometimes compared this to lightning, suggesting they sensed a connection between the two phenomena. However, Without a systematic way to measure or reproduce the effects, their understanding remained limited to curiosity. Similarly, lightning itself was often the subject of speculation. Philosophers like Aristotle attempted to describe natural phenomena, but their explanations were rooted more in philosophy than in empirical science. Aristotle, for example, believed that lightning was caused by hot, dry exhalations from the earth that ignited in the upper atmosphere. While this idea was incorrect, it demonstrates the effort to place natural events within a logical framework rather than leaving them entirely to myth. In China, scholars also observed strange attractive forces in natural materials, though they did not directly connect them to electricity as we define it today. Chinese writings from around 2,000 years ago describe how lodestones attracted iron, and though this was magnetism rather than electricity, it revealed that invisible forces of attraction and repulsion were part of nature. Over time, these ideas would intertwine with the study of electricity, since both involved unseen powers that acted at a distance. The fascination with lightning also produced religious rituals and protective practices. Many cultures built monuments or conducted ceremonies to honor the gods of thunder in hopes of avoiding their wrath. Temples were sometimes struck by lightning, and these events were often interpreted as signs or omens. For example, in ancient Rome, lightning strikes were carefully recorded by priests who treated them as messages from the gods and adjusted rituals or political decisions accordingly. In Northern Europe, sacred trees struck by lightning were revered and in some cases turned into shrines. These responses show that even without science, people recognized the significance of lightning and sought to give it meaning in their lives. As centuries passed, the mysterious phenomena of static electricity and lightning remained curiosities rather than subjects of rigorous study. Without instruments to measure forces or theories to explain them, progress was impossible. Yet the seeds of discovery had been planted. By noticing that amber could attract small objects, or that lightning could strike with devastating power, ancient civilizations had unknowingly begun the story of electricity. They may not have had words like electrons, circuits, or voltage, but they experienced the raw manifestations of these concepts in ways that were powerful enough to shape myths, religions, and medical practices. Thus, the early encounters with static and lightning were the first sparks of curiosity in a journey that would eventually lead to the discovery of electricity. They revealed that the world contained hidden forces beyond the visible, and that these forces had the potential to influence human life in profound ways. What began as simple observations of amber and storms would one day evolve into a systematic science capable of illuminating cities, powering machines, and transforming civilization itself. The ancients could never have imagined the full consequences of their curiosities, but their wonder at the invisible powers of nature was the first essential step toward the discovery of electricity. The journey from ancient curiosities to the first attempts at systematic experimentation with electricity began in the Renaissance and early modern period, when scholars started to move beyond mythological explanations and instead sought natural causes for the strange forces of attraction and lightning that had fascinated humanity for centuries. The rediscovery of classical texts, combined with a growing culture of experimentation, encouraged thinkers to test natural phenomena in ways that were more methodical and measurable. One of the earliest pioneers in this age of experimentation was William Gilbert, an English physician and natural philosopher, who in 1600 published his groundbreaking work De Magnete. Although the title focused on magnetism, Gilbert also included some of the earliest serious studies of electrical effects. He repeated the ancient observation that amber, when rubbed, could attract small objects. But he expanded the range of materials he tested and noted that substances such as sulfur glass and sealing wax exhibited similar properties. Gilbert coined the term electricus from the Greek electron, meaning amber, to describe these attractive forces, and in doing so gave birth to the modern word electricity. He concluded that this force was distinct from magnetism, though at the time he could not fully explain its cause. His experiments marked the beginning of electricity as a separate field of inquiry, rather than a curiosity tied only to amber or lightning. In the decades that followed, other scholars built upon Gilbert's observations by trying to categorize and understand the sparks and attractions produced by rubbing various materials. Otto von Guericke, a German scientist and inventor, is remembered for creating one of the earliest machines that could generate static electricity. Around 1660, he constructed a large sulfur globe mounted on an axis that could be rotated and rubbed with the hand to produce sparks and glowing discharges. Observers were astonished at the bright flashes and crackling sounds the device produced, and Guericke's machine represented the first attempt to create electricity artificially on demand, rather than simply observing it in nature. His experiments also revealed the existence of electrical repulsion as well as attraction, since small objects not only clung to the charged globe, but were also pushed away under certain conditions. This discovery hinted that electricity was more complex than previously thought. As the 17th century gave way to the 18th, scientists across Europe began to design similar devices to generate and study static electricity. The English natural philosopher Francis Hauksbee improved on Guericke's design by creating a glass globe that, when rotated and rubbed, produced bright bluish glows inside the evacuated sphere. These glows were eerie and beautiful, and Hauksbee demonstrated them publicly at meetings of the Royal Society in London. Audiences were fascinated by the strange lights, which seemed almost magical, but Hauksbee himself emphasized that they were natural phenomena that could be studied and explained. His work not only deepened interest in electricity, but also linked it to the study of gases, light and vacuum physics fields that would later connect with electrical research in unexpected ways. The age of experimentation also produced new theories about the nature of electricity, even if many of them were later shown to be incorrect. Some believed that electricity was a kind of invisible fluid that could flow from one body to another. Others proposed that it was a special kind of matter or essence residing within certain materials. The lack of precise instruments made it difficult to test these ideas, but speculation and debate encouraged further research. Stephen Gray, an English experimenter, made important contributions in the early 1700s when he discovered that electricity could be conducted over long distances through certain materials by suspending wires and cords made of silk or hemp. He showed that the electrical charge could travel far from its original source. This distinction between conductors and insulators was a crucial breakthrough, because it revealed that electricity was not confined to the material that produced it, but could be transmitted across space. Another key figure was Charles François de Sistonnais Dufay, a French scientist who in the 1730s proposed that there were two types of electricity, which he called vitreous, produced by rubbing glass, and resinous, produced by rubbing resinous substances like amber. He observed that objects with the same type of charge repelled each other, while objects with opposite charges attracted one another, though his terminology would later be replaced by Benjamin Franklin's positive and negative charges. The recognition of two distinct forms of electrical behavior represented an important step forward in understanding. Public demonstrations of electrical experiments became popular across Europe in the 18th century, turning electricity into both a scientific field and a source of entertainment. Traveling lecturers carried electrostatic machines to cities and towns, where they astonished audiences by making sparks jump from fingertips or causing small objects to levitate. Some even performed tricks, such as igniting alcohol vapors with electrical sparks, or charging human bodies so that sparks could be drawn from their noses or fingertips. These spectacles captured the imagination of the public and showed that electricity was not only a theoretical curiosity, but also a force that could be harnessed in dramatic ways. By the mid-18th century, scientists began to develop ways to store electricity for later use, which allowed for more controlled experimentation. The invention of the Leyden jar around 1745 by Peter van Musschenbroek in the Netherlands and Ewald Georg von Kleist in Germany provided the first practical capacitor capable of storing large amounts of static charge. This device consisted of a glass jar lined inside and out with metal foil and fitted with a metal rod connected to the inner layer. When charged, the jar could deliver a powerful spark upon discharge, astonishing those who witnessed it. The Leyden jar became a standard tool in electrical laboratories, and for the first time, scientists could accumulate and release significant quantities of electricity on demand. The age of experimentation thus transformed electricity from an ancient curiosity into a field of active scientific research. Through trial and error, scholars discovered that electricity could be generated, transmitted, stored, and manipulated. And though they did not yet understand the true nature of the phenomenon, they laid the foundation for the breakthroughs of Franklin, Volta, Faraday, and others who would follow. The sparks from amber and the flashes from rotating globes hinted at a deeper reality, waiting to be uncovered, and by daring to experiment systematically, early modern scientists turned hidden forces of nature into the beginnings of a science that would one day reshape the world. When the history of electricity is traced back to its foundations, the name of William Gilbert stands out as one of the most important pioneers, because he was the first to treat the mysterious, attractive forces of amber and lodestones, not as curiosities or magical powers, but as subjects of systematic study, grounded in observation and experiment. Born in 1544 in Colchester, England, Gilbert trained as a physician and rose to prominence as the personal doctor of Queen Elizabeth I. Yet his passion for natural philosophy led him to conduct wide-ranging investigations into the forces of magnetism and electricity, which culminated in his seminal book, De Magnete, published in 1600. Although the title emphasized magnetism, the text contained some of the earliest organized research on electrical phenomena, and in many ways, it marked the birth of electrical science as a discipline distinct from mere speculation. Gilbert began by replicating and expanding upon the ancient Greek observation that amber rubbed with cloth could attract small objects, such as feathers or straw. Unlike his predecessors, however, he did not stop with amber, but systematically tested a wide range of substances, including glass, sulfur, sealing wax, and gems. He discovered that many of these materials displayed the same attractive properties after being rubbed, and in order to describe them, he coined the term electricus, derived from the Greek word for amber electron. This introduction of a specific term was more than a linguistic novelty, because it separated the electrical effect from magnetism, which had long been known through lodestones. Gilbert emphasized that while magnets attracted iron continuously without any preparation, the electrical effect required friction and acted on lighter objects. This distinction laid the groundwork for recognizing electricity and magnetism as related but separate phenomena. Gilbert also created simple instruments to aid his experiments, such as the versorium, which was essentially a lightweight metal needle pivoted on a base so that it could rotate freely. When brought near an electrically charged object, the needle would turn and align itself with the invisible force. Though rudimentary, the versorium was the first electrical measuring instrument, and it allowed Gilbert to study attractions systematically rather than relying on casual observation. He noted that the strength of the effect diminished with distance, and that only certain materials exhibited it, while others, such as metals, did not unless insulated. These observations may seem basic today, but at the time they represented a dramatic leap forward, because they showed that electrical forces could be studied with precision and consistency. In De Magnete, Gilbert also advanced the idea that the Earth itself was a giant magnet, which explained the behavior of compasses and the alignment of magnetic poles. This insight into magnetism, although not directly electrical, was revolutionary because it framed natural forces as properties of the physical world rather than mystical emanations from the heavens or divine intervention. By treating electricity and magnetism as natural forces governed by laws, Gilbert shifted the study of these phenomena into the realm of science. His careful method of experimenting, recording results, and drawing conclusions influenced later natural philosophers and earned him the reputation of being one of the fathers of modern experimental science. Gilbert's theories extended beyond attraction and magnetism because he speculated on the nature of the electrical and magnetic forces themselves. He believed that each body capable of producing attraction had what he called an effluvium, a kind of invisible emission that acted on nearby objects. While this idea was not accurate, it provided a framework for thinking about action at a distance, which was a difficult concept for natural philosophers of his time. The notion that objects could influence one another without direct contact challenged the Aristotelian worldview and pointed toward a new physics that would later be refined by figures such as Newton and Maxwell. The influence of Gilbert's work spread quickly throughout Europe and inspired generations of scientists to continue the exploration of electrical and magnetic phenomena. His emphasis on empirical testing encouraged others to build machines, to generate larger amounts of static electricity, and to devise new experiments that would expand knowledge of the subject. Although he lacked the tools to measure current or voltage and had no concept of electrons, his insistence on careful observation and his introduction of new terminology created a foundation upon which later discoveries could be built. Beyond his direct contributions, Gilbert's work symbolized a turning point in how natural phenomena were studied during the Renaissance. Whereas earlier thinkers often relied on philosophical reasoning or appeals to ancient authority, Gilbert placed experimentation at the center of inquiry. He did not dismiss the observations of the ancients, but he insisted on testing them and expanding them with his own experiments. This empirical attitude was in line with the broader scientific revolution that was emerging in Europe at the time, and his research on electricity became one of the earliest examples of how systematic experimentation could reveal hidden truths about nature. It is also important to recognize the limitations of Gilbert's work because they highlight how far science still had to go. He did not develop a theory of electrical conduction, nor did he discover that metals could transmit electrical charges when properly insulated. He did not conceive of electricity as a flow of particles or charges, but rather as a property associated with certain materials. Yet even these limitations were significant because they set clear boundaries for what had been discovered and what remained unknown. By articulating what electricity could and could not do, Gilbert challenged others to refine and expand his theories. The legacy of William Gilbert lies not only in the specific experiments he conducted, but also in the way he framed the study of electricity as a legitimate branch of natural philosophy. By coining the word electricus, by distinguishing electrical attraction from magnetism, and by creating instruments to detect and measure the effects, he established the first vocabulary and methodology for electrical science. His work resonated long after his death in 1603, influencing thinkers like Robert Boyle, Otto von Guericke, and later Benjamin Franklin. Every spark observed in laboratories, every Leyden jar discharged, and every theory of electrical fluids can trace its intellectual ancestry back to Gilbert's decision to take amber's strange attraction seriously. In the story of the discovery of electricity, Gilbert represents the moment when curiosity began to transform into science, when the unexplained wonders of static attraction were brought into the realm of systematic study. His contribution was not the discovery of electricity in the modern sense, but the discovery that electricity was a phenomenon worthy of study in its own right, subject to laws that could be investigated, tested, and understood. This recognition was the true birth of electrical science, and it ensured that future generations would continue the quest to unlock the secrets of the forces hidden in amber sparks and lightning bolts. Among the figures most closely associated with the discovery and popularization of electricity, Benjamin Franklin holds a central place because he not only conducted famous experiments that captured the imagination of the public, but also introduced concepts and terminology that shaped the language of electrical science for centuries to come. Franklin was not a professional scientist in the strict sense, but a printer, statesman, and polymath whose curiosity about the natural world led him to perform some of the boldest experiments of the 18th century. By the time Franklin began his investigations, European scientists had already developed machines to generate static electricity, such as rotating glass globes and the Leyden jar, which stored electrical charge. Public demonstrations of sparks and shocks had become fashionable amusements across the continent, but Franklin sought to move beyond spectacle and toward understanding. He wanted to know whether the sparks produced in laboratories were fundamentally the same as the lightning that flashed across the sky, and this guiding question led to one of the most legendary experiments in scientific history. In 1752, Franklin performed what would become known as the kite experiment. Accounts differ on the exact details, and some historians debate whether Franklin himself carried it out exactly as described. But the essence of the experiment is clear. Franklin constructed a simple kite from silk which could withstand rain and attached to it a metal wire. At the base of the string, he tied a key and held the string with a silk ribbon to insulate himself from direct contact. During a thunderstorm, Franklin flew the kite and observed that the fibers of the string began to stand out as if charged. When he brought his knuckle close to the key, he witnessed a spark jump across the gap, demonstrating that the lightning storm had electrified the apparatus. With this daring act, Franklin showed that lightning was not a supernatural phenomenon or a distinct kind of fire, but rather the same electrical force observed in laboratory experiments. This conclusion was revolutionary because it unified natural and artificial electricity under a single concept. From this and related experiments, Franklin proposed several important ideas. He suggested that electricity consisted of a single fluid that could be in excess or deficit within a body. When an object had more of this fluid than its natural amount, he called it positively charged, and when it had less, he called it negatively charged. Although the terminology of positive and negative was somewhat arbitrary, it became a lasting convention, still used today. Franklin also introduced the idea of conservation of charge, noting that when electricity seemed to appear in one place, it must have been taken from another. These conceptual tools provided a coherent framework for understanding electrical interactions and guided further research across Europe. Franklin's insights were not purely theoretical, because he also recognized practical applications of his discoveries. Most famously, he invented the lightning rod, a simple metal rod mounted atop buildings and connected by a conductor to the ground. The purpose of the rod was to provide a safe pathway for lightning strikes, thereby protecting structures from fire. At a time when lightning often caused devastating blazes in wooden buildings, this invention was of enormous importance. Franklin installed lightning rods in Philadelphia, and their effectiveness quickly spread their adoption across the colonies in Europe. His invention demonstrated that electricity was not merely a curiosity, but a force that could be harnessed to safeguard human life and property. The kite experiment and Franklin's writings also helped to elevate the study of electricity within the broader scientific community. His letters and reports were published in Europe, where they attracted the attention of prominent figures such as the French physicist Charles de Coulomb and the Swedish scientist Anders Celsius. The French Academy of Sciences praised Franklin's work and recognized his contributions as central to the progress of natural philosophy. This recognition was unusual for a colonial American, and it underscored the global significance of his achievements. Franklin's fame as an electrical experimenter became so widespread that when he later traveled to France as a diplomat during the American Revolution, he was already celebrated as a man who had captured lightning from the heavens. Yet the kite experiment also carried immense risk, because lightning is incredibly powerful and can instantly kill anyone struck by it. Franklin was fortunate that he did not attempt to draw a bolt of lightning directly into his kite, but rather collected charge from the surrounding storm. Other scientists who tried to replicate the experiment without proper precautions were not so lucky. In 1753, Georg Wilhelm Richtmann, a Russian physicist, was killed in St. Petersburg when lightning struck his apparatus during a similar test. His death served as a grim reminder of the dangers involved and highlighted Franklin's narrow escape. Nevertheless, the experiment's symbolic power endured because it epitomized the Enlightenment spirit of daring inquiry and the willingness to risk personal safety in the pursuit of knowledge. Franklin's work also influenced the philosophical understanding of electricity. By showing that lightning and laboratory sparks were the same, he erased the boundary between celestial and terrestrial phenomena. This was a profound shift, because for millennia, lightning had been regarded as the weapon of gods, or the expression of divine anger. Franklin revealed it to be a natural force governed by the same laws as everything else in the physical world. In this way, his kite experiment not only advanced science, but also undermined superstition, and reinforced the Enlightenment vision of a universe knowable through reason and experiment. In addition, Franklin's terminology and ideas created a shared language for scientists. The concepts of positive and negative charge, conservation of charge, and the electrical fluid theory provided a framework that could be built upon, even as later discoveries revised or replaced aspects of his model. For example, although modern science understands electricity not as a fluid, but as the movement of electrons, the idea of charge and its conservation remains fundamental. Franklin's practical approach, linking theory with application, also inspired later inventors and engineers who sought to harness electricity for communication, light, and power. The legacy of Franklin's kite experiment lies not only in its immediate results, but also in its enduring symbolism. It demonstrated that with simple tools and clear reasoning, even the most mysterious forces of nature could be investigated by human hands. It bridged the gap between natural spectacle and scientific explanation, and it showed that electricity was a universal force present both in the laboratory and in the heavens. From the sparks of amber to the bolts of lightning, Franklin's experiment marked the moment when electricity was fully recognized as a natural phenomenon that could be studied, harnessed, and ultimately mastered. In the broader story of the discovery of electricity, Franklin stands as the figure who gave the field its first coherent framework and who transformed electricity from an amusing curiosity into a cornerstone of natural philosophy. The story of electricity reached a decisive turning point at the end of the 18th century with the work of Alessandro Volta, the Italian physicist who invented the first true battery, and by doing so opened the door to continuous electrical currents that could be studied, harnessed, and eventually used to transform society. Before Volta, electricity had largely been confined to static charges produced by friction machines or stored briefly in Leyden jars, and while these devices were impressive, they could not provide a steady, reliable flow of electricity for experimentation or practical use. Volta's invention of the voltaic pile in 1800 changed everything because it allowed electricity to move as a constant current, and it remains one of the most significant breakthroughs in the entire history of science. Volta's path to the battery began with a famous scientific controversy involving his contemporary Luigi Galvani, who in the 1780s had been experimenting with frog legs. Galvani observed that when a scalpel touched the exposed nerves of a dissected frog, the legs twitched violently as if alive. He believed that the muscles of the animal contained what he called animal electricity, a vital force produced by living tissue. This interpretation gained great attention because it suggested that electricity and life itself were intimately connected, and many saw in Galvani's work a glimpse of the mysterious energy of vitality. Volta, however, was skeptical of this idea. He repeated Galvani's experiments and noticed that the twitching often occurred when two different metals were used to connect the frog's nerves, such as copper and zinc. Volta concluded that the electricity did not originate in the animal, but rather in the metals themselves, and that the frog's leg was simply serving as a sensitive detector of the current. This disagreement between Galvani's theory of animal electricity and Volta's theory of metallic electricity became one of the most famous debates in the history of science. And although both men contributed important insights, it was Volta's explanation that ultimately prevailed. Determined to prove his case, Volta began constructing stacks of alternating discs of zinc and copper, separated by pieces of cloth soaked in salt water or dilute acid. He discovered that when the metals were arranged in this sequence, they produced a continuous electrical flow that could be detected and even spark small currents. This apparatus, which became known as the voltaic pile, was the world's first true battery, and it immediately revolutionized the study of electricity. For the first time, scientists could generate a steady current instead of brief discharges, and this allowed for entirely new kinds of experiments. The pile was simple in construction, but ingenious in principle, because it relied on the chemical reactions between the metals and the electrolyte to produce electrical energy. Each pair of zinc and copper discs created a small potential difference, and by stacking many pairs together, Volta was able to multiply the effect and produce currents strong enough to shock experimenters or decompose chemical compounds. The announcement of the voltaic pile in 1800 created a sensation across Europe. Volta presented his invention to Napoleon Bonaparte, who recognized its significance and honored him with titles and prizes. Scientists quickly adopted the battery for research, and within months, remarkable new discoveries were being made. William Nicholson and Anthony Carlisle used a voltaic pile to split water into hydrogen and oxygen in the first demonstration of electrolysis, showing that electricity could directly drive chemical reactions. Humphrey Davy soon employed increasingly powerful batteries to isolate new chemical elements such as potassium, sodium, calcium, and magnesium, which had never before been seen in pure form. The link between electricity and chemistry was thus firmly established, giving rise to the field of electrochemistry. Volta's invention also had profound implications for the understanding of electricity itself. Until then, electricity had been regarded primarily as a static force, but the voltaic pile revealed it as a dynamic phenomenon, capable of flowing like a current. This shift in perspective laid the foundation for later work by Michael Faraday and James Clerk Maxwell, who would explore the connections between electricity magnetism and electromagnetism. The unit of electrical potential, the volt, was named in Volta's honor to commemorate his pivotal role in advancing the field. Beyond the laboratory, the battery represented the first step toward practical applications of electricity. Though Volta himself did not foresee its technological uses, his invention provided the essential tool for experiments that would eventually lead to telegraphs, electric lighting, and motors. The voltaic pile was bulky and limited in power, but it demonstrated the principle that chemical reactions could be harnessed to produce continuous electricity, a principle that remains at the heart of modern batteries, from the ones in smartphones to those that power electric cars. Volta's achievement also highlighted the importance of scientific debate and skepticism. By challenging Galvani's interpretation and carefully testing alternatives, Volta demonstrated the value of questioning assumptions and relying on empirical evidence. In hindsight, both men were partly correct because living tissues do produce electrical signals as Galvani believed. But Volta's demonstration that metals and electrolytes could generate electricity independently was the crucial breakthrough that unlocked practical experimentation. Their debate sparked decades of research into bioelectricity and electrochemistry fields that remain vital today. The legacy of Alessandro Volta extends far beyond the invention of the battery, because his work epitomized the spirit of the scientific revolution, in which careful observation, bold experimentation, and theoretical insight combined to reveal new forces of nature. He showed that electricity could be generated not just by friction or lightning, but by reproducible chemical processes, and in doing so, he transformed it from a fleeting curiosity into a controllable resource. The voltaic pile was the engine that powered the next century of discoveries, and it remains one of the greatest inventions in human history. In the grand narrative of the discovery of electricity, Volta stands as the figure who provided the essential key that turned electricity into a continuous and usable phenomenon. His pile opened pathways to chemistry, physics, and engineering that would shape the modern world. By stacking simple discs of metal and cloth, he created not just a new device, but a new era in science. The voltaic pile was more than a battery, it was a gateway into the future, and it secured Volta's place as one of the most influential figures in the history of electricity. The discovery of continuous electricity through Volta's battery had opened vast new possibilities for experimentation, but it was the work of Michael Faraday in the 19th century that truly unlocked the deeper relationship between electricity and magnetism, and laid the foundation for nearly every electrical technology that would follow. Faraday was born in 1791 in humble circumstances in London, the son of a blacksmith with little formal education. Yet, through determination and curiosity, he rose to become one of the most influential experimental scientists of all time. His life itself symbolized the power of observation, persistence, and imagination in the advancement of science. Faraday began his career as an apprentice bookbinder, which gave him access to scientific texts that he eagerly read. Eventually, he attended lectures by the great chemist Humphrey Davy at the Royal Institution and impressed him enough to secure a position as his assistant. From there, Faraday embarked on decades of groundbreaking research, first in chemistry and later in electricity and magnetism. His most enduring legacy was his demonstration that electricity and magnetism were not separate forces, but intimately connected aspects of a single phenomenon. Before Faraday, it was known that electricity could produce sparks, shocks, and chemical effects, and that magnets exerted forces on iron and compass needles. But the link between the two was unclear. In 1820, Hans Christian Ørsted discovered that an electric current could deflect a magnetic compass needle, showing that electricity could produce magnetic effects. This discovery electrified the scientific community, but it was Faraday who would explore it fully and reveal the broader principles. Faraday asked whether the reverse was also possible. Could magnetism produce electricity? He constructed ingenious experiments to test this idea, using coils of wire magnets and galvanometers, sensitive instruments that could detect small currents. After many attempts, he succeeded in 1831 by demonstrating electromagnetic induction. When he moved a magnet in and out of a coil of wire, he observed that a current was generated in the wire. And when he moved the wire near a stationary magnet, he saw the same effect. This was the birth of the principle of induction, and it showed that changing magnetic fields could create electricity. Faraday's discovery of induction was one of the most important in the history of science, because it provided the principle underlying the electric generator and transformer. For the first time, it was possible to conceive of producing electricity on a large scale, not by chemical batteries, but by mechanical motion. If a coil of wire could generate a current when moved near a magnet, then a machine could be built to rotate coils continuously within magnetic fields, thereby producing continuous electricity. This principle became the foundation of power generation and remains the basis of nearly all electrical power plants in the world today, whether driven by steam turbines, waterfalls, or wind. Faraday's experiments did not stop at induction. He introduced the concept of lines of force to describe the way magnetic and electric effects spread through space. While other scientists often treated forces as abstract mathematical quantities acting at a distance, Faraday visualized them as physical fields that extended around magnets and charges. He drew diagrams of curved lines emanating from poles and charges, and these images helped him conceptualize how energy was transmitted. Although Faraday lacked advanced mathematics, his field concept profoundly influenced later scientists, especially James Clerk Maxwell, who translated Faraday's ideas into the elegant equations that form the basis of modern electromagnetism. Faraday also invented practical devices that demonstrated his principles. His experiments with rotating magnets and conductors produced the first simple electric motor and generator, showing that electricity could be converted into mechanical energy and vice versa. These devices, though primitive, illustrated the immense potential of electromagnetism for technology. Faraday's motor used a wire carrying current that rotated around a magnet, while his generator used a rotating disc cutting through magnetic lines of force to produce current. These were direct ancestors of the machines that would power the industrial world in the coming decades. Beyond induction, Faraday explored the chemical effects of electricity, developing the laws of electrolysis, which describe how electric current can decompose chemical compounds. His precise experiments with water acids and salts showed that electrical forces were responsible for chemical bonding, and he introduced terms like anode, cathode, electrode, and ion, which remain in use today. In this way, he deepened the unity between physics and chemistry, linking electricity, magnetism, and matter itself. Faraday's work also extended to optics, as he demonstrated that magnetic fields could influence light, a phenomenon now called the Faraday effect, which hinted at the deep connections between all forces of nature. What made Faraday extraordinary was not only the range of his discoveries, but also his ability to think experimentally and conceptually, without relying heavily on mathematics. He had an intuitive grasp of physical phenomena, and he built devices that revealed hidden principles in simple, clear ways. His notebooks reveal a mind constantly probing, testing, and refining ideas, and his insistence on careful observation became a model for experimental science. His lectures at the Royal Institution were also legendary, because he had a gift for communicating complex ideas to general audiences through vivid demonstrations. These lectures inspired generations of scientists and members of the public alike, and helped to popularize science as a pursuit open to everyone. The impact of Faraday's discoveries on society cannot be overstated. By revealing the principle of electromagnetic induction, he made possible the generation and distribution of electricity on a scale large enough to power industries, homes, and cities. Every time a turbine spins in a power plant or a generator turns in a windmill, it is Faraday's law of induction at work. The modern world of electric lighting, communications, and machines owes its existence to his insights. Faraday himself remained modest and uninterested in wealth or fame. He declined a knighthood and turned down burial in Westminster Abbey, preferring a simple life dedicated to science and faith. His humility, combined with his genius, made him one of the most admired figures in the history of science. In the larger story of the discovery of electricity, Faraday represents the moment when electricity ceased to be a laboratory curiosity and became a universal force of nature harnessed for practical use. His discovery that magnetism could generate electricity transformed the field, and his vision of lines of force led to the modern concept of fields, which underlies much of physics. Faraday showed that electricity and magnetism were two sides of the same coin, and he set the stage for Maxwell Einstein and countless others to expand upon his work. His legacy endures in every generator motor and transformer and in every illuminated city powered by the principles he revealed. The discoveries of Michael Faraday had revealed that electricity and magnetism were deeply connected forces, and his vision of invisible lines of force filling space suggested that there was a deeper unity waiting to be uncovered. Yet Faraday was not a mathematician, and though he had an extraordinary intuition about nature, he could not express his insights in the formal language of equations. It was James Clerk Maxwell, the Scottish physicist born in 1831, who translated Faraday's experimental findings into a coherent mathematical framework, and in doing so created the modern theory of electromagnetism. Maxwell's work did not simply describe electricity and magnetism separately, but unified them into a single set of equations that revealed their interdependence and predicted entirely new phenomena, including the existence of electromagnetic waves. His achievement was one of the great triumphs of 19th century science, often compared to Newton's Principia, because it provided both a unifying theory and a predictive tool that transformed physics forever. Maxwell began his education in mathematics at a young age and quickly demonstrated a remarkable ability to apply abstract reasoning to physical problems. When he turned his attention to electricity and magnetism in the 1850s, he found the field dominated by experimental results collected by Faraday, Ørsted, Ampere, and others, but lacking a rigorous theoretical framework. Faraday's lines of force were seen by many scientists as useful visual aids, but not as real physical entities. Maxwell, however, took Faraday's vision seriously and sought to describe it quantitatively. He proposed that space itself was filled with fields which could carry energy and transmit forces without direct contact between bodies. This was a revolutionary idea because it replaced the old notion of action at a distance with the concept of a medium that propagated influences through continuous interactions. Maxwell's great contribution came in the 1860s when he formulated a system of equations that expressed the relationships between electric fields, magnetic fields, charges, and currents. These equations showed that a changing electric field produced a magnetic field, and a changing magnetic field produced an electric field. The two phenomena were not separate, but dynamically linked in a self-sustaining cycle. From this relationship, Maxwell predicted the existence of waves composed of oscillating electric and magnetic fields that could travel through space at a finite speed. When he calculated the speed of these waves using known values for electrical and magnetic constants, he found that it matched the measured speed of light. This stunning result led Maxwell to conclude that light itself was an electromagnetic wave, a vibration of the combined electric and magnetic field traveling through space. With this realization, Maxwell unified optics, electricity, and magnetism into a single theory, showing that phenomena once studied separately were all aspects of the same underlying reality. The implications of Maxwell's theory were profound. It explained why light exhibited properties such as reflection, refraction, and polarization, because these were natural behaviors of electromagnetic waves. It also predicted the existence of electromagnetic radiation beyond the visible spectrum waves of longer or shorter wavelength that were invisible to the human eye. This prediction was confirmed decades later when Heinrich Hertz generated and detected radio waves in the 1880s, proving Maxwell's theory correct. Today, we recognize that radio waves, microwaves, infrared light, ultraviolet rays, X-rays, and gamma rays are all part of the electromagnetic spectrum, unified under Maxwell's framework. Maxwell's equations not only explained existing phenomena, but also provided the theoretical foundation for nearly every electrical technology that emerged in the late 19th and 20th centuries. The development of radio telecommunications, radar television, and eventually wireless internet all depended on the understanding that information could be transmitted through electromagnetic waves. Electric power systems, including alternating current generators and transformers, also relied on the mathematical framework that Maxwell established. In this sense, his equations became the blueprint for the modern technological world. Maxwell's work also reshaped physics itself. By showing that light was an electromagnetic wave, he suggested that all forces might eventually be unified under a common framework. His field concept replaced the old mechanical view of forces acting instantaneously across empty space, and laid the groundwork for the later development of Einstein's theory of relativity and quantum field theory. Albert Einstein himself credited Maxwell's equations as the most profound and influential work of physics in the 19th century, remarking that the theory of electromagnetism inspired his own search for deeper unifications. Despite the enormous significance of his work, Maxwell remained a modest and gentle man, devoted to teaching and research. He held academic positions at King's College London, and later at Cambridge, where he became the first director of the Cavendish Laboratory, a centre that would produce many of the greatest discoveries in 20th century physics. His students and colleagues admired him for his clarity of thought and his ability to connect mathematics to the tangible realities of experiment. Though he died young at the age of 48 in 1879, his legacy endured through the power of his equations, which remain at the core of physics education and research to this day. In reflecting on Maxwell's role in the discovery of electricity, it becomes clear that he represented the transition from the age of experiment to the age of theory. Faraday had uncovered the principles of induction and envisioned lines of force. Maxwell gave those visions mathematical form and revealed their full implications. He showed that electricity and magnetism were not isolated curiosities, but aspects of a single electromagnetic field, capable of carrying energy across the universe. His work turned electricity from a collection of laboratory effects into a universal law of nature, and it opened the path to technologies that would shape human civilization. Maxwell's equations remain one of the most beautiful and powerful achievements in science, elegant in form and vast in consequence. They stand as a testament to the ability of mathematics to capture the workings of nature and to reveal hidden unities beneath apparent diversity. In the grand narrative of the discovery of electricity, Maxwell provided the mathematical foundations that transformed an experimental science into a coherent theory. And in doing so, he gave humanity not only understanding, but also the tools to harness one of the fundamental forces of the universe. By the late 19th century, the discoveries of Volta, Faraday, and Maxwell had given humanity both the means to generate electricity and the theoretical framework to understand its behavior. Yet the question of how to deliver electricity to homes and industries on a large scale remained unresolved. This challenge gave rise to one of the most dramatic rivalries in the history of technology, known as the War of Currents, in which two brilliant but very different inventors, Thomas Edison and Nikola Tesla, clashed over the best system for distributing electrical power. Edison was already a celebrated inventor by the 1880s, famous for creating the phonograph and developing practical incandescent light bulbs. He envisioned an electrical future powered by direct current or DC, in which electricity flowed steadily in one direction, from a generator to consumers. Edison built the first DC power stations in New York, including the Pearl Street Station in 1882, which provided electricity to a small district of Manhattan. His system worked for short distances and low voltages, and it demonstrated that electric lighting could replace gas lamps, transforming urban life. However, DC had a fundamental limitation because it could not easily be transmitted over long distances without significant loss of power. This meant that power stations had to be built close to consumers, which was expensive and impractical for widespread electrification. Nikola Tesla, by contrast, was a Serbian-born inventor who had emigrated to the United States in 1884. Brilliant, imaginative, and eccentric Tesla believed that alternating current, or AC, was the superior solution. In an AC system, the current periodically reverses direction, and its voltage can be increased or decreased using transformers. This meant that electricity could be transmitted at very high voltages across long distances with minimal loss, and then step down to safe levels for use in homes and businesses. Tesla's ideas were initially dismissed by Edison, who considered AC dangerous and impractical. But Tesla found an ally in the industrialist George Westinghouse, who recognized the commercial potential of AC and purchased Tesla's patents for AC motors and transformers. Together, Tesla and Westinghouse began building AC power systems that directly challenged Edison's DC empire. The rivalry escalated into a public battle during the 1880s and 1890s, as both sides sought to convince the public and investors of their superiority. Edison launched a campaign to portray AC as unsafe, emphasizing the dangers of high voltage. In one notorious episode, Edison's associates electrocuted animals, including dogs and even an elephant, with AC currents to dramatize the risks. Edison also promoted the use of AC in the first electric chair to execute criminals, hoping to associate it permanently with death and danger. Tesla and Westinghouse, however, continued to refine AC technology, demonstrating its efficiency and safety when properly managed. Tesla's development of the polyphase AC motor, a device capable of running on alternating current without needing constant adjustments, was a key breakthrough because it allowed factories and machines to be powered directly from AC systems. The decisive moment in the War of Currents came with the contract to supply power to the 1893 World's Columbian Exposition in Chicago. Westinghouse and Tesla won the bid and used AC generators and lighting systems to illuminate the fairgrounds with over 200,000 light bulbs, dazzling millions of visitors and proving the reliability of AC on a massive scale. This success was followed by the construction of the Niagara Falls power plant, completed in 1895, which used Tesla's AC system to transmit electricity over long distances to Buffalo, New York. The project was a triumph of engineering and demonstrated beyond doubt that AC was the future of electrical distribution. Edison's DC system quickly faded in importance, and within a few decades AC became the global standard. The War of Currents was not merely a technical debate, but a clash of personalities and philosophies. Edison was pragmatic, relentless, and business-oriented. He valued practical solutions that could be commercialized quickly and often worked by trial and error. Tesla, by contrast, was a visionary with a deep theoretical understanding inspired by Faraday and Maxwell's field theories. He imagined a world of wireless communication, global power transmission, and technologies far ahead of his time. While Edison achieved great financial success, Tesla struggled to maintain stable funding and often lived in poverty despite his extraordinary contributions. The outcome of the War of Currents shaped the modern electrical world. AC power became the backbone of national and international grids, enabling electricity to reach vast numbers of people and fueling the second industrial revolution. Factories, homes, and cities were electrified, allowing for new industries, mass production, and urban growth. At the same time, the rivalry highlighted the social and ethical dimensions of technological change. Edison's fear tactics showed how business competition could distort scientific debate, while Tesla's idealism revealed both the promise and the peril of visionary thinking without financial grounding. In hindsight, both men were indispensable to the history of electricity. Edison's contributions to practical devices, such as the light bulb, the phonograph, and the early power stations, showed how electricity could be integrated into daily life. Tesla's work on AC systems, induction motors, and wireless transmission provided the infrastructure and vision for large-scale electrification. Together, they symbolized the tension between invention and innovation, between immediate practicality and long-term vision. The war of currents also foreshadowed later debates in technology, where competing systems vied for dominance, such as VHS versus Betamax, or more recently renewable energy versus fossil fuels. It underscored the fact that scientific truth alone does not determine technological outcomes, but that economics, politics, and public perception also play decisive roles. The eventual victory of AC was not simply because it was technically superior, though it was, but also because Westinghouse and Tesla managed to demonstrate its advantages in dramatic public venues like the Chicago Exposition and Niagara Falls. In the broader story of the discovery of electricity, the war of currents represents the moment when electricity moved from the laboratory and small-scale demonstrations to the infrastructure of modern society. It was the turning point when electrical science became electrical industry, transforming daily life on a global scale. The lights of Chicago and the power of Niagara Falls marked the triumph of alternating current, but they also symbolized the fusion of science, engineering, and commerce in shaping the modern world. Tesla and Edison may have been rivals, but together their legacies ensured that electricity became not just a scientific discovery, but the lifeblood of the 20th century. With the victory of alternating current in the war of currents and the growing understanding of electromagnetic principles, the 19th century entered a period in which electricity was no longer confined to laboratories or exhibitions, but began to be harnessed for practical use on a scale that transformed communication industry and daily life. One of the earliest and most important applications was the telegraph, which revolutionized how humans could send information across long distances. Before the telegraph, communication relied on messengers, horses, ships, and visual signals, such as flags or smoke, and the speed of information was limited by the speed of transportation. The invention of the electrical telegraph in the 1830s by Samuel Morse in the United States and Charles Wheatstone and William Cooke in Britain changed this permanently. By sending pulses of electric current along wires and using codes to represent letters, telegraph systems allowed messages to be transmitted instantly over vast distances. The laying of transatlantic cables in the 1850s and 1860s connected continents, and for the first time allowed Europe and America to exchange information in minutes rather than weeks. The telegraph became the nervous system of the industrial world, linking markets, militaries, and governments, and demonstrating the immense power of electricity as a tool of human progress. Following the telegraph came the telephone, invented by Alexander Graham Bell in 1876. The telephone converted sound waves into electrical signals transmitted through wires and then back into sound on the receiving end. Unlike the telegraph, which required trained operators to encode and decode Morse code, the telephone allowed direct voice communication. It spread rapidly and became one of the defining technologies of the late 19th and early 20th centuries, reshaping business, social life, and global connectivity. Both the telegraph and telephone depended on reliable electrical currents and demonstrated how electricity could bridge physical distances, transforming human relationships. While communication was the first domain to be electrified, lighting was the next great frontier. For centuries, artificial light had been provided by candles, oil lamps, and gas lamps, all of which were limited, inefficient, and hazardous. The development of electric lighting promised cleaner, safer, and brighter illumination. Humphrey Davy had created the first electric arc lamp in the early 19th century by passing a current between two carbon rods, producing an intense light. But arc lamps were too bright and impractical for homes. The challenge was to create a lamp that was small, durable, and economical. Many inventors attempted to design incandescent lamps, using filaments heated by electric current to glow without burning. It was Thomas Edison and Joseph Swan who, in the late 1870s, achieved the first practical incandescent bulbs by using carbonized filaments in evacuated glass bulbs. Edison, in particular, perfected the system, not just the bulb itself, but the entire infrastructure of generators, wiring sockets, and switches that made electric lighting feasible for widespread use. His Pearl Street station in New York City in 1882 supplied power to hundreds of lamps and demonstrated how electricity could replace gas lighting in urban environments. The spread of electric lighting was rapid and transformative. Cities illuminated by electric lamps became safer. At night, businesses could operate longer hours, and homes gained a new level of comfort and convenience. Electric light also had profound cultural and psychological effects because it altered human patterns of work and leisure, extending the day and changing perceptions of time itself. Factories lit by electricity could run shifts around the clock, and urban nightlife flourished in ways previously impossible. The glow of electric lights became a symbol of modernity and progress. Electricity was also harnessed for power in industries. Motors driven by electric current began to replace steam engines in factories because they were more efficient, cleaner, and easier to control. Machines could be powered directly by electric motors connected to wires rather than by cumbersome belts and shafts driven by central steam engines. This flexibility allowed factories to be designed in new ways and contributed to the Second Industrial Revolution. Elevators powered by electric motors made skyscrapers possible, reshaping cities with vertical architecture. Electric trams and trains provided efficient urban and regional transport, transforming mobility and accelerating the growth of modern cities. The practical harnessing of electricity also encouraged the development of measuring instruments, switches, fuses, and safety devices that made systems reliable and secure. Innovations such as transformers, developed by William Stanley in the 1880s, enabled the transmission of AC power at high voltages over long distances, and then its safe distribution at lower voltages to consumers. This infrastructure created the foundation of modern power grids, capable of serving millions of people. The rise of electric utilities transformed electricity from an experimental novelty into a commodity measured, sold, and consumed on a daily basis. Beyond communication, lighting and power, electricity found applications in entertainment and culture. Early experiments with electrical signals led to the invention of the phonograph, motion picture projectors, and eventually radio. Electric amplification made concerts and theatres larger and more spectacular. The public increasingly associated electricity with excitement, wonder, and modern life. World's fairs in cities like Paris and Chicago displayed dazzling arrays of electric lights, machines, and appliances, showcasing electricity as the force of the future. The transformation brought about by harnessing electricity was not without challenges. The rapid growth of electrical systems required enormous investment and raised issues of regulation, safety, and access. Accidents from faulty wiring or overloaded circuits were common in the early years, and public fear sometimes slowed adoption. Yet the advantages were so great that electrification advanced relentlessly across Europe, North America, and eventually the entire globe. By the early 20th century, electricity had become the essential utility alongside water and gas, and societies began to imagine a future fully powered by this invisible force. In the grand story of the discovery of electricity, the era of harnessing it for telegraphs, light bulbs and motors represents the moment when theory and experiment gave way to widespread application. The sparks observed in amber and the currents generated by batteries had now grown into networks that encircled cities and continents. The telegraph shrank the world, the telephone gave it a voice, and electric lighting illuminated its nights. Factories and transport powered by electricity reshaped economies and daily life. What had once been a mysterious curiosity had become the engine of modern civilization and the symbol of progress. Electricity was no longer hidden in storms or laboratories. It flowed through wires, lighting streets, ringing telephones, and driving machines. This harnessing of electricity was one of the greatest transformations in human history, and it laid the foundation for the electrified world we inhabit today. The discovery and harnessing of electricity stand among the greatest achievements in human history, because no other scientific breakthrough has altered the course of civilization so dramatically or so completely. What began with the simple observation of amber attracting straw in ancient Greece developed through centuries of curiosity, experiment, and invention until it became the foundation of modern society. The legacy of this discovery is visible in every home, every city, and every industry, because electricity is now the invisible lifeblood of the modern world. Its impact extends across science, technology, culture, and even philosophy, reshaping how humanity understands itself and its place in nature. The first and most obvious legacy of electricity is the transformation of daily life. Electric lighting turned night into day, extending human activity beyond the limits of the sun. Streets illuminated by electric lamps became safer and more vibrant. Homes became places of comfort, with lighting appliances and heating systems powered by electricity. The ability to control light and power at the flick of a switch gave people a sense of mastery over their environment, unprecedented in history. Workplaces, too, were revolutionized. Factories driven by electric motors no longer depended on steam engines or water wheels and could be located anywhere wires could reach. Production became more efficient and flexible, enabling mass production on a scale that defined the Second Industrial Revolution. Communication was also transformed. The telegraph, telephone, and later radio and television all depended on electricity to transmit signals across vast distances. Messages that once took days or weeks to travel could be sent in seconds. This shrinking of the world through electrical communication created a new global interconnectedness. Markets, governments, and families could share information instantly, changing politics, commerce, and culture. Today, the internet, the most advanced form of electrical communication, has become the nervous system of the planet, linking billions of people in real time. None of this would have been possible without the long journey of discovery that began with static sparks and Leyden jars. Electricity also revolutionized medicine. Hospitals became equipped with electric lighting, sterilization systems, and diagnostic tools. X-rays discovered by Wilhelm Röntgen in 1895 relied on electrical apparatus to reveal the hidden structures of the human body, transforming diagnosis and surgery. Later developments, such as electrocardiograms, defibrillators, and medical imaging, all depended on electricity. The legacy of discovery thus extended beyond industry and commerce to the preservation of human life itself. In science, electricity provided both a subject of study and a tool of exploration. Theoretical advances by Faraday and Maxwell laid the groundwork for modern physics. Maxwell's equations not only unified electricity, magnetism, and light, but also inspired the development of Einstein's theory of relativity and later quantum mechanics. Electricity became the means by which laboratories could power experiments, from particle accelerators to electron microscopes. In this sense, the discovery of electricity opened the door not only to technology, but also to deeper knowledge of the universe. The cultural impact of electricity was equally profound. Electric light and power became symbols of modernity, progress, and even national pride. Cities competed to showcase electric lighting at world fairs, and exhibitions dazzling visitors with brilliant displays that seemed almost magical. The Eiffel Tower, illuminated by electricity during the 1889 Paris Exposition, or the White City of the 1893 Chicago Columbian Exposition, stood as monuments to human ingenuity and the promise of a new age. Writers, artists, and filmmakers incorporated electricity into their work as a metaphor for power, energy, and transformation. Electricity thus became woven into the cultural imagination as the force that defined the modern world. The legacy also includes economic and political dimensions. The rise of electric utilities created vast industries and monopolies, shaping the structure of modern economies. Companies such as General Electric and Westinghouse grew out of the inventions of Edison and Tesla and became global giants. The spread of electrification was often used as a measure of national progress, and governments invested heavily in building power grids to modernize their societies. In rural areas, the arrival of electricity transformed agriculture, enabling irrigation, refrigeration, and mechanization. Electrification campaigns in the 20th century became central to economic development worldwide. Yet the legacy of electricity is not purely positive, because it also created new dependencies and challenges. The demand for electrical power grew rapidly and required enormous infrastructure with environmental consequences. The burning of coal and oil to generate electricity contributed to air pollution and climate change. The reliance on centralized power grids created vulnerabilities to blackouts and political control. The very success of electricity in powering civilization thus raised new questions about sustainability and responsibility. Even so, humanity continues to search for cleaner and more efficient ways to generate electrical power through hydroelectric dams, nuclear plants, solar panels, and wind turbines. The philosophical legacy of electricity is perhaps less visible, but equally important. by revealing that lightning and sparks were not divine or mystical, but natural phenomena governed by laws. Electricity helped to shift humanity's worldview toward a more scientific and rational understanding of nature. It reinforced the Enlightenment belief that through observation, reason, and experiment, humans could unlock the secrets of the universe. At the same time, the discovery of electricity showed that unseen forces could shape reality in profound ways, challenging the limits of human perception and imagination. Ultimately, the legacy of the discovery of electricity is that it transformed humanity from a species limited by muscle fire and simple tools into one that could reshape the planet with machines, networks, and technologies powered by invisible currents. Every aspect of modern civilization, from communication and transportation to health and entertainment, is built upon the foundation laid by centuries of curiosity and experimentation. Franklin's kite, Volta's pile, Faraday's coils, Maxwell's equations, Edison's bulbs, and Tesla's currents were milestones on a path that led to the electrified world we inhabit today. Electricity is no longer merely a discovery, it is the environment in which modern life exists. It flows through wires in walls, charges the devices in our pockets, lights the screens we stare at, and drives the machines that sustain global economies. The story of electricity is the story of how humanity learned to control one of nature's fundamental forces, and in doing so, transformed itself. The legacy of discovery is not complete, because the future will bring new ways of generating, transmitting, and using electricity. But the foundation has been set by centuries of struggle, triumph, and imagination. The invisible spark, discovered in amber, became the force that powers civilization, and it remains one of the greatest testaments to the power of human curiosity and ingenuity.